Hello, I'm Paul Bass, the Senior Product Manager at Sybase for Parallel Products. Welcome to our discussion on parallel database servers. Dr. Ron Hu will join me later. Ron is a system architect at Sybase in the Parallel and Distributed Products Group. We're going to do the presentation in 3 sections. The first section will be an overview of parallel relational database management systems with a brief discussions about why they exist and what they're good for. In the second section, Ron's going to talk about the different technical approaches for parallel relational database management systems with both hardware and software discussions. I will then come back in the third section and discuss Sybase's navigation server as a specific example of a parallel relational database management system implementation. The whole reason for parallel database management is performance, performance, performance. High performance database management for high capacity database requirements. The amount of information that needs to be stored has grown from megabytes to gigabytes to terabytes. With the advent of parallel hardware platforms, we have the opportunity to greatly speed up and scale up performance for applications with these high database capacity requirements. There are also opportunities with the parallel environment for some high availability features. Let's talk more about scale up versus speed up. Speed up is pretty simple to explain. The goal of speed up is to greatly reduce response time by applying more hardware resources to the same amount of data. Conversely, scale up is when we take a workload, increase the amount of data, increase the number of users, and increase the number of transactions and still achieve the same good response time. What are the environments that these parallel database management systems are good for? Definitely decision support. Whether we call it data mining, data warehousing, or just plain decision support, parallel DBMS is very good for speeding up queries, getting those responses to be much quicker. And that's both for analytical processing, where we need to process a lot of data to get an answer, and information retrieval, where maybe each request doesn't have to access much data, but there's still a lot of data in the system. Since there's really no such thing as just a read-only decision support system, we also need to do very efficient batch processing. Loading data, archiving data, updating, adding new data, deleting old data. These are all very important, as well as getting quick answers to the queries. It's also apparent that these large parallel systems can support online transaction processing. However, the demand for these online transaction processing systems is lagging behind the demand for decision support systems, but it'll be there. The ultimate goal is to be able to do both decision support and online transaction processing on the same computer platform at the same time. It'll be a while before we get there, but we will be able to do it. Okay, at this point, I'm going to turn it over to Ron to do a technical overview about the different types of parallel database implementations.
Hello, in this section, we are going to look at various technical approaches to parallel database servers. We are going to cover parallel hardware architecture, parallel software architecture, levels of parallelism, parallel query optimization, and the pros and the cons of parallelism. In a parallel database server, we have both hardware and software. People frequently mix hardware architecture with software architecture, but actually there is a difference. First, let's describe 3 well-known parallel hardware architectures. The first one is shared memory hardware architecture. In this hardware platform, we have multiple CPUs, and all the CPUs share the same memory. Here, it will be easier to do load balancing among the CPUs and easier to do system administration. However, for this hardware platform, the scalability will be limited to the number of CPUs in a machine. With current hardware technology in system bus bandwidth, we expect no more than 32 CPUs in a shared memory hardware platform. And This kind of hardware platform cannot tolerate single point failure in the processing node. Typical examples of the shared memory hardware platform are the popular SMP, symmetric multiprocessor boxes. The second hardware architecture is the shared disk, in which we have multiple nodes sharing the same set of disks. Each node has its own local main memory and can be an SMP box. However, different nodes do not share any common memory, and they exchange control messages through an interconnection network. In this hardware, there is no automatic load balancing among the processing nodes, and it is more complex to do system administration. But scalability will be better because we have multiple CPUs in the multiple node configuration. In case one processing node is down, we still have other nodes up and running to continue operation. Therefore, a shared disk hardware has higher availability than a shared memory hardware. Typical examples of the shared disk hardware are today's cluster platforms, such as Digital's VMS cluster and Sun's Spark 1000 cluster. The third parallel hardware architecture is the shared nothing hardware. In this hardware architecture, each node is in charge of its own local main memory and its local disk. One node cannot access another node's main memory or disk directly, and all the nodes are connected through an interconnection network. By the way, for today's technology, each node can be an SMP box. For a shared nothing hardware, there is no automatic load balancing among the processing nodes, and it is more complex to do system administration. However, in terms of scalability, research has shown this hardware architecture is the most scalable one. This has to do with each node being able to process most data locally without moving it around. Therefore, we can have many nodes as long as the interconnection network has enough bandwidth. In terms of availability, this hardware platform is better than the other two, since more hardware components can better tolerate hardware failures. Typical examples of the shared nothing hardware platforms are AT&T's 3600 systems and IBM's SP2. In our discussion of various hardware architectures, we talk about CPUs and main memory. Now we are going to discuss the parallel software architectures. Instead of CPU and main memory, we will talk about software processes and database buffers. Software processes are the operating system processes, and they are controlled by an OS scheduler. As for database buffers, they are the memory space allocated by database software. A database software usually allocates a certain amount of memory space depending on its need. The main reason to keep a database buffer is because it is usually expensive to have disk access. Whenever we fetch a data block from disk, we normally want to cache it into the database buffer for subsequent references, so that we do not need to go to disk to get it for every access. Now, we are going to describe three parallel software architectures. The first one is the shared memory software architecture. In this architecture, there is only a single database buffer used by all the running process, and there is also a single database storage accessible by all the processes. A shared memory software normally has low implementation complexity and low processing overhead. The second parallel software architecture is the shared disk software. In this architecture, there is a single logical database storage accessible by all the running processes. And the key difference between this one and the shared memory software is in this architecture, each running process has its own database buffer. When a data block is fetched from disk into database buffers, the same data page may appear in more than one buffer. And when a running process changes the data page in its local buffer, other running processes will have an absolute copy of the data page in their database buffers. This is the so-called buffer incoherence issue. Some database vendors use a distributed log manager to solve this issue. Due to a large performance overhead required to maintain buffer coherence, a shared disk software limits the scalability of a parallel database system. The third parallel software architecture is the shared nothing software. In this architecture, each running process is in charge of its own database buffer and its own database storage. And the same data page can appear in only one local buffer because the same data page cannot appear in more than one buffer. There is no buffer incoherence issue. Therefore, we can minimize the interference among the running processes. All the running processes communicate through messages to exchange data or control information. We have described three parallel software architectures. Let's see how flexible or portable these three software architectures are. As shown on the screen, you can see that shared memory software can run only on shared memory hardware platforms, since it has no mechanism to access remote memory in non-shared memory hardware. As for the shared disk software architecture, it can run on both shared memory hardware and shared disk hardware. As for the shared nothing software architecture, it can run on all three parallel hardware platforms, as long as the database engine can allocate the database buffer for each running process. And the running processes just communicate the messages among them. The running processes do not care where messages come from, whether from within the same node or from different nodes. Clearly, the shared nothing software is the most portable one to run on various hardware platforms. Let's talk about different levels of parallelism now. The first one is the inter-transaction parallelism. Here, we can have multiple transactions executed concurrently in a system. Today, most commercial database systems support inter-transaction parallelism, as long as the system has a locking mechanism to allow multiple transactions running in parallel. The second level of parallelism is the inter-query parallelism. In a single transaction, we may have multiple queries. If there are some queries which can be run independently, then we can run those queries concurrently without affecting each other in order to reduce the response time for a given transaction. The third level of parallelism is the intra-query parallelism. This parallelism can be further classified into two types. The first one we call pipeline parallelism. A user query may be decomposed by database engine into multiple steps, and we can allocate multiple processing threads for the steps, one thread for each step, to shorten query response time. As shown in this diagram, a user query needs to scan the table first and then sort the filter out record. These two steps, scan and sort, can be pipelined together. This means that the output of the scan can be used as the input of the sort. If we utilize two threads to pipeline these two steps together, then we can overlap the execution of scan and sort operation so that query response time can be reduced. The second type of intra-query parallelism is called partition parallelism. This means that we can partition a large table into multiple slices. When a user's query comes in, it is sent to all the slices to run in parallel, and later the result is merged together. There is no doubt that the relational database theory has made partition parallelism a popular mechanism for parallel database servers. This is because the simple table layout defined in relational theory makes it very easy to partition large tables. Between these two inter-query parallelism, partition is more effective than pipeline. Why? Most SQL queries can normally be decomposed into no more than 10 database steps. By pipelining these steps together, then pipeline parallelism has a potential to speed up a query 10 times. As for partition parallelism, it is especially useful for large tables. When you have a large table with 200 gigabytes, you can partition this table into 100 slices with 2 gigabytes each, and then run the query on these 100 slices concurrently. Then you have a potential to speed up the query 100 times. Here, I want to point out that partition parallelism and pipeline parallelism are complementary to each other. A good database server can certainly have both. Now, let's move to the next topic, parallel query optimization. When a user's query comes in, the query optimizer in database engine will evaluate numerous options and then try to choose the best and the cheapest access plan for the query. So, as you can see, the performance of a database system will be highly dependent on the query optimizer's performance. Research has shown that for parallel database servers utilizing partition parallelism, it is important that the query optimizer generate an adaptive query plan to deal with data skew, that is, uneven data distribution. In real-world applications, it is almost impossible to avoid some kind of uneven data distribution among the nodes in the parallel database system. For example, we may have one node receiving much more records than other nodes. Even we have every node receiving the same number of records, when a user's query comes in, there could be some kind of selectivity skew. I mean, one node may have much more qualified records than other node. So clearly, it is difficult to avoid data skew completely. Then, in order to alleviate the data skew, the best way is to design the query optimizer so that it can produce an adaptive query plan based on the local data characteristics and distribution. For a parallel database server, the query optimization task can be divided into two levels. At the system level, we can just apply the general relational optimization techniques. For example, make sure selection and projection operation occur before the join operation. At the load level, we will take the diverse data distribution within each node into account. Then, each node will choose the optimal query access plan based on its local data distribution. In a parallel environment, the slowest component will determine the job response time. Therefore, it is important to make each node have its optimal execution plan. Let me show you 3 cases where the adaptive query plan can be useful. In the first case, since tables are partitioned, each node can decide independently whether or not it will use full table scan or index method when it tries to access table records. That is, The first node may use full table scan to access its portion of data. The second node may use index method. The third node may use table scan, etc. There is no single fixed access method applied to all the nodes. Clearly, the right choice for table access within a node is 100% dependent on the local distribution, not on the entire data distribution in the whole system. In the second case, for join operation with nested loop join algorithm, one table has to be the inner table, and the other has to be the outer table. The right assignment for inner table and the outer table can affect the join performance significantly. When we join table A and the table B in a skewed distribution situation, we may assign table A as the inner table in the first node, table B as the inner table in the second node, etc. Again, local data distribution is sufficient to decide the right table assignment for join in each individual node. The third case is for systems supporting more than one join algorithm. We know nested loop join is good for small tables. Hash join and sort merge join are good for large tables. The adaptive query plan allows each node to decide which join algorithm to use based on the local data distribution within each node. Of course, the benefit of the adaptive query plan are not limited to these three cases only. Research has shown that the adaptive query plan can effectively alleviate data skew problems and quite often bring an order of magnitude speed up for real-world applications running on large configuration database systems. Now, we are going to address the pros and the cons of parallelism from the performance point of view. Paul mentioned earlier that the reason we want to have parallelism in the database engine is to have high performance database management for high capacity requirements. Apparently, parallelism provides effective access to very large databases. Parallelism also provides effective speed up and scale up for many database operations, such as loading, scanning, index creation, insertion, deletion, update, join operation, etc. Without parallelism, it is impossible to collect large data and access them to get the answers in a timely fashion. But on the other hand, parallelism is not free. In order to achieve parallelism, a parallel server has to introduce some overhead in execution. It is okay to have overhead in a parallel system. The issue is the degree of overhead. In the following, I will talk about some types of overhead frequently observed in parallel database servers. The first one is the query startup overhead. When a user's query comes in order to execute it in parallel, we may need to send the same query to more than one node, or we may need to create new processing threads in a node. Either case introduces query startup overhead. The second type of overhead is execution, synchronization, or interference overhead. For example, to deal with a buffer incoherence issue in a shared disk software, the distributed log manager introduces overhead to synchronize multiple running processes. And to perform updates in more than one node in a shared nothing architecture, we have to use the two-phase commit to synchronize the operation. Both cases are typical examples of interference overhead. The third one, data movement overhead. When we try to process a query in parallel on multiple slices, each slice may return some records. In order to form the final result, we need to move the records from individual slices to a central place. Also, to perform join operation in a shared nothing software, sometimes we have to shuffle records. Both merging results and shuffling records for join are the overhead introduced by parallelism. The fourth one is a data skew overhead introduced by partition parallelism. We discussed this overhead when we described parallel query optimization. The last one is the processing skew overhead introduced by pipeline parallelism. In this case, one thread may do more work than other thread, and then the thread doing more work will delay all other threads with less work. Depending on how a parallel database server can control the degree of overhead, different systems will show different performance behaviors. Of course, the goal is to have performance gain much larger than performance overhead. This completes my discussion on various technical approaches to parallel database servers. In the next section, Paul will talk about the approach used in the Sybase navigation server.
Navigation Server is an example of a shared nothing software implementation to achieve parallel relational database processing. It works in a client-server environment just as a single Sybase SQL server does. Navigation Server was jointly developed by Sybase and AT&T Global Information Solutions. It is a collection of processes working together to speed up and scale up applications. It is based on the premise of horizontal partitioning of tables. Each table is separated into different physical partitions in 3 different ways. We can have range partitioning, which is alphabetic subsets separated by an appropriate key, or hash partitioning, which applies a hashing algorithm on the appropriate key to randomly place tables into different subsets into different physical partitions. It also has the option of what we call schema partitioning. This is where we have small tables where there's no need to partition the table at all. A global directory knows and has the information that specifies how these tables are partitioned. Each partition is assigned to its own relational database engine. In the case of Navigation Server, this is the Sybase SQL Server. When SQL commands and instructions come into the Navigation Server environment, they can be translated into parallel SQL. This parallel SQL and the plans associated with this parallel SQL is now applied to these multiple partitions with their associated SQL servers, again, to speed up the performance. One more look at how tables are partitioned is this diagram showing where tables are spread across multiple physical domains. Each of these rectangles could be a collection of disk drives. As you can see, some tables can be partitioned across all of the partitions, some can be spread across a subset, and for small tables, they don't need to be spread at all. Now, how do we determine which tables need to be partitioned and how much software and hardware do we need to support a particular application? Part of Navigation Server's environment is a utility called the configurator. The inputs into the configurator are the logical database design, the application's capacity requirements, the transaction requirements, the response time requirements, and your choice of hardware components. The configurator simulates this environment to produce software and hardware configurations and performance estimates. It also has the capability of constraining the hardware environment so you can make different choices on performance versus cost. After a Navigation Server system is implemented, statistics can be collected, passed to the configurator for analysis, and used to improve the partitioning, software, or hardware configuration. Let's talk now about the different components, the basic components of Navigation Server. Again, Navigation Server is a collection of processes that communicate to each other through messages. As Ron said earlier, this is called shared nothing. The first process I want to talk about is the DBA server. This is the brains and the smarts behind Navigation Server. This is the process that optimizes and compiles all the SQL commands that come into the system. With the assistance of a process we call the schema server, it interprets these commands, figures out the best way to execute them, stores the plans, and if needed, actually decomposes and creates new SQL that can be used by the underlying SQL Server engines. The next process I want to talk about is the control server. The control server is the dispatching unit. This is what receives requests from the client applications, initiates and monitors the parallel execution, sends those parallel requests to all the participating engines, and when they're done, the control server merges and sends the results back to the requesting client application. The next process is the data server. The data server is comprised of a SQL server and a split server. The SQL server is the Sybase SQL server that treats its partition as if it were its own independent database. The split server's role will become apparent when later we talk about how joins work. Let's now look at how these processes work together. For compilation of SQL in the form of stored procedures, requests come into the environment to a control server. It is passed to the DBA server for compiling and optimization. The resulting plans are stored in a global directory, and the new SQL is passed to the SQL servers for their local optimization. These two levels of optimization can be very beneficial to reduce the effects of data skew and processing skew. No matter how hard we try to separate the tables evenly and have them distributed evenly, you can have one partition that gets bigger than the others. An individual SQL server can optimize for its partition. Because remember, in a parallel environment, you're only as fast as the slowest component. In the next diagram, we want to talk about the kind of work that can take place in a single partition. The control server receives the request and simply sends it to the correct partition, and the work gets done. Results are then returned to the application through the control server. There is a little bit of overhead from the control server, but not much. For transaction scale-up, imagine that many control servers are processing many requests, sending them to different SQL servers to get the work done. This is a really good example of inter-transaction parallelism. Next, I want to talk about speeding up a single piece of work. Operations and commands that are done in parallel by Navigation Server include table scans, table joins, updates, deletes, inserts, data loading, backup, restore, creating indexes, and reorganizing tables. Requests come to the system to a control server. If the request is not a stored procedure, the control server will pass the command to the DBA server for optimization. If it is a stored procedure, the control server first looks to see if it has the plan in its memory. If not, it requests a copy of the plan from the DBA server. The control server now essentially sends the same request to all the participating SQL servers. They work together to speed up the response time. This is a good example of intra-query parallelism. This speed up also works if we join two tables that are partitioned the same way on the same key. If we need to join two tables that are not partitioned the same way, the system needs to redistribute subsets of these tables into temporary tables and different partitions, so they then can be joined in place. This is where the split server comes to work. The split server controls and manages the movement of data from one partition to another and getting it into these temporary tables. There are really four different types of joins. The first one is the in-place join when two tables are partitioned the same way on the same key. There are also two types of what we call redeclustering or redistribution joins. Let's use as an example the classic employee table, department table join. If I have partitioned the employee table by employee number and the department table by the department number, I can't join these two tables in place. With the first redecluster option, a subset of the employee table is copied and repartitioned by department number into the partitions of the department table where it can then be joined by department number. Let's look at the second example, which is redecluster 2. The optimizer notes that the subsets are relatively small, So we move subsets of both tables into a new home, whether that home is a single partition or a multiple partition, and do the join there. A final example is what we call replicating. A subset of one table is replicated or copied onto the partitions of the other table for joining. Even with this data movement, substantial speedup can be gained over doing the join with a single database engine and a single partition. This is an important time to re-stress the point that shared nothing software implementations in this relational database environment can be applied to any type of parallel hardware platform. All of these processes and partitions that we've been talking about could be spread across one to many nodes. As an example, if we have 8 partitions, we could apply those 8 partitions in one SMP box. We could also split them in half and implement them onto 2 SMP boxes working together in a cluster environment. Or we could split it even further onto 4 nodes with 2 partitions each. This is a great example of the flexibility and scalability of shared nothing software architectures. These systems also need to be managed. Navigation Server has a manager that runs on a separate workstation that hides the complexity of dealing with multiple nodes, multiple processes, and multiple partitions. It controls the backup and restore, it executes stored procedure, and manages the different logs. Another component of Navigation Server is its high availability architecture. The DBA server is constantly being monitored by an alternate DBA server. If the master DBA server should fail, the alternate DBA server will restart the master. The DBA server monitors the control servers. If a control server fails from a software failure, it will be restarted by the DBA server, so the processing can continue. Similarly, the control server monitors the split servers and SQL servers and will restart them if they indeed fail. In a multi-node configuration, if an entire hardware node fails, the DBA server will restart all the processes that work on that node on a secondary node so that processing can continue. This allows for quick recovery and high availability. So what's in the future for Navigation Server? We're going to constantly work on improving its performance. We'll add some additional partitioning methods, such as replicating small tables ahead of time, so there's not as much work to do when we have joins that can take advantage of the replicated tables. We will also partition indexes so that non-clustered indexes can be partitioned in a different way than the actual base table. We will always make the optimizer ever smarter. We will continue to improve the throughput for transaction processing support. We will continue to improve the utilities. So, we've overviewed parallel database management systems. We've looked at the hardware and software architectures, and we've examined the Sybase Navigation Server as a specific example. I hope you found our presentation useful. Thank you very much for your interest.